There are two different ways to draw an enantiomer. So if I'm looking and draw the mirror image, 5, 6, 7, 8, I need my 8 carbons, and then I'm going to reflect. So I have an OH on a wedge here on carbon 2. I'm going to put an OH on a wedge here. I'm going to put my CH3 on a wedge here, and then I put this methyl group on a dash. That's one way to draw an enantiomer. The other way to draw an enantiomer is to draw the longest carbon chain, 2, 4, 6, sure, that's 8 carbons, and then just draw it as it is from left to right, except wherever there is a dash, put a wedge, and where there's a wedge, put a dash. So this methyl group would get to be on a wedge now because it's on a dash in the original molecule. This methyl group would now be on a dash, and the alcohol group would also be on a dash. These are equivalent compounds here. It's just a different way to draw it. So if we draw a diastereomer of this compound for number 3, 1, 2, 3, 4, 5, 6, 7, 8 carbons long again, then I'm going to have the same groups for 2, and then I'm going to switch one of my groups. That is a diastereomer. There are a number of different answers for this one. This is just one example of a diastereomer for this compound. Number 4, for a compound with 6 chiral centers, how many possible stereoisomers are there? Well, it's 2 raised to the n, where n is the number of chiral centers. So 2 raised to the 6th, which is 64. There are 64 possible stereoisomers. Now, without knowing what the compound is, we don't know how many of those are meso compounds. So there are a possible 64 stereoisomers for that compound. Number 5. With a total of 8 stereoisomers for a compound with 3 chiral centers, because 2 to the n is 8. If this is the first stereoisomer, draw the only enantiomer. Okay? So the only enantiomer of this compound, we could draw it as we did above for number 2. We could draw it as a mirror image, or we could draw it by 2, 4, 6, 7, 2, 4, 6, 7. Changing every one of our chiral centers. Now that's the way that I prefer to do it in a situation like this, because it's easier for me to keep track of my chiral centers. So this is an enantiomer of the isomers shown. So now if we continue on and draw a diastereomer of this first isomer, that's what we're referring to here, by changing the leftmost chiral center, then I go with my 7 carbon chain, the leftmost chiral center, I'm going to change the configuration of and retain the configuration of the other chiral centers. So that is a diastereomer of our initial isomer. So now we're going to draw a different diastereomer of the first stereoisomer by changing the middle chiral carbon's configuration. So I retain this one, and I change this one. Now we're going to draw another diastereomer, the first stereoisomer, by changing the rightmost chiral carbon's configuration. And I just noticed that they wanted the mirror image of each of these as well. So I went back and filled in my mirror images. So you see the 8 isomers that we've found with this compound that has 3 stereocenters. Number 6, what's the relationship of these following Fischer projections? Are they the same? Are they enantiomers, or are they diastereomers? Is 1 stereocenter here, but 2 of our groups match, but 2 do not. Therefore, they must be opposite in rotation, or opposite in their stereochemistry. So these should be enantiomers. Now, just for practice sake, I'm going to name or assign the R and the S. So 1 goes to the OH, 2 goes to the ethyl, 3 goes to the methyl. I'm going to rotate my leftmost molecule. I'm going to rotate this to the right or clockwise. H is on the vertical, so this is an R configuration. And over here I have, on the right, I have a counterclockwise rotation. H is on the vertical, so this is an S, and that does make them enantiomers. So for B, we have 2 that match and 2 that don't. But if I hold it, if I hold this and spin the molecule around, they might be the same. I think this one's worth naming. So we have 1 for our OH, 2 for our ethyl, 3 for our methyl group. I'm going to rotate to the right. H is on the vertical. I'm rotating to the right or clockwise. H is on the vertical. These are these same compounds. For C, I'm going to name these 2. So 1 for our OH, 2 for our ethyl, 3 for our methyl. On the compound or the asymmetric center on the left, I rotate clockwise. H is on the vertical. This is an R configuration. And on the right, I'm going to rotate counterclockwise. H is on the horizontal. So that makes this an R configuration as well. So these are the same compound. For D, let's see, I'm going to start with the top configuration here. Number this 1, the rest of the molecule is 2, the methyl group is 3. I rotate this counterclockwise, H on the vertical. That makes the top one an S configuration. And the bottom, 1, 2, 3, H is on the horizontal. I'm rotating counterclockwise. That makes this an R configuration. So here, the top asymmetric center, I have 1, 2, 3. I'm going to rotate counterclockwise. H is on the horizontal. That makes this an R configuration. And 1, 2, 3. I'm going to rotate clockwise. H is on the horizontal. That makes this an S configuration. Now, immediately, just looking at it, you want to say they're enantiomers, but we need to analyze this one a little bit deeper. So if I put all of my H's on the horizontal, the way that this one has H's on the horizontal, and all I'm going to do is rotate around here. It's still an S configuration, but what you find out is that these are the same molecules. You might want to make these 2 with your model kit and prove it to yourself. Number 7, draw an enantiomer of each of the following. In order to draw an enantiomer, what we're doing is we are changing the order of the rotation around the asymmetric center. So I'm going to do CH3 here and OH here, and that's an enantiomer of A. So for B, I'm just going to draw the mirror image, just like this. To draw a diastereomer of each of the following, for A, that's kind of a trick question. It only has 1 stereocenter, so it doesn't have a diastereomer. It only has an enantiomer. And for B, we're going to hold one of the asymmetric centers the same and flip the other one. So I'm going to flip the one on the bottom and then keep this one the same. So there's one diastereomer. Another diastereomer would be if I kept the bottom the same and flipped the top, mirror image the top. And finally, for number 9, let's identify some possible meso compounds. So the quick way to identify a meso compound is to look for a plane of symmetry. A has a plane of symmetry through these 2 carbons right here. So this is a meso compound. This is not. It does not have a plane of symmetry. This is a meso compound. It has a plane of symmetry. This is not no plane. This one does. This one does. This compound does have a plane of symmetry, but it does not have any chiral centers because both sides of the ring are equivalent. So there are no chiral centers. We can't call it a meso compound. For B, it might be easier if we look at this, well, if we draw this compound here this way, and then we keep one of the bromines here. So what I've done is I've rotated around this bond. The other bromine comes out towards us. So this is not meso. This compound, again, let's draw it this way. Keep this bromine here, rotate around this bond. Then you get this bromine reflecting back as well. So there is a plane of symmetry on this one. So this is a meso. There is no plane of symmetry here. It's very common for students to want to draw the plane right through here. But notice how this is a methyl group, not a bromine, and methyl and bromine are very different. So there is no plane here, not a meso compound. On first inspection, we want to draw a plane of symmetry right here through the bromine, but the methyls do not line up. Therefore, this is not a meso compound. This, however, is a meso compound. The plane goes right through that alcohol group. We have two equivalent sides, so this is meso.